We'll take a few minutes here to review percent composition. But again, this is usually kind of a topic that makes sense. So people catch on really quick. Percent composition is really just the mass of a particular element or maybe a particular ion divided by the mass of the whole particle, the whole compound, times 100 to get a percentage. It makes sense. It's the part divided by the whole. You could get something like this first one. What is the mass percent of ammonium ions in ammonium sulphide? Whenever I'm dealing with a compound, I definitely need the formula. Ammonium is a polyatomic NH4, charge +1. Sulphide with the IDE is just regular sulfur -2. So to make this neutral, we must put parentheses around ammonium because we need two groups of ammonium. I want to know the mass percent of ammonium ions. So I want the mass of all the ammonium ions divided by the mass of the whole compound. Piece of cake. So here's all my ammonium, which again, it's important that I have the formula written correctly so I know there are 2 ammonium ions per molecule. So I'll plug this in my calculator. 2 times nitrogen and 8 times the hydrogen. 4 times 2 for 8. Remember, this 2 gets distributed to everybody on the inside of the parentheses. So 2 nitrogen, 8 hydrogen gives me a mass of about 36.10. 36.10. There's the mass of all the ammonium ions. There are 2 of them. That's a plus. There we go. Divided by the mass of the compound. So all I have to do is add the sulfur. So that's going to give me about 68.17 grams of ammonium sulphide. We'll plug this in our calculator, multiply by 100 to get a percentage. And we are good to go. Now, as far as sig figs, all the numbers that I have down are constants. I personally did not measure the molar mass of any of these atoms. So if you get something like this and you have to round to sig figs now, you're always kind of safe with a percentage going 2 decimal spots. So if I don't have any other indicators for sig figs, let's plug this in and say 52.96. 0.96% ammonium ions by mass. If you have other data, then I would always go with whatever lab measurements are given. But in this case, it's all constants off the periodic table. 2 decimal spots on a percent is safe. So a little over half the mass comes from the ammonium ions and a little bit over half coming from the sulfur ion. That's easy, right? I hope so. Here's a way that you could use this. I really do like ones like this second one. This is something I've used quite a bit throughout the year. How many grams of lead could be extracted from a 25.80 gram sample of lead chloride? This almost gets into a little stoichiometry too, where like you could do these calculations one of 2 ways. We could, write the balanced equation for the decomposition of lead chloride into lead and chlorine, or we could use percent composition. We need to write the formula for this compound, lead 2 chloride, and then let's do this. Let's think about it as percent composition, as what percent of this sample is lead? Because then that should be the same as the mass of lead coming from the sample. So lead 2, meaning the lead is charged +2, plus, thinking about it, there we go, +2 on the lead, chlorine's -1. So my compound is lead with 2 chlorines. Got to make it neutral. All right, let's do percent composition. Let's see what percent of this mixture, or this compound, I should say, what percent of it is lead? Percent lead. So I look up lead on the periodic table. 207.2. My periodic table really only leaves 1 decimal spot for lead. So I'm okay there. Otherwise, I'd go at least 2 decimal spots on any molar masses. So let's add the 2 chlorines. The compound, about 278 point, wow, actually it's 0.1. I'll leave it like that. Unless you get something like this where they just happen to come out as 1 decimal spot. That's the lead chloride compound. Now, if I wanted to, I could multiply this by 100, but I'm going to leave it as a decimal. At this point, for sig figs, again, it's all constants off my periodic table, but I noticed that the lab data given is 25.80 grams, which eventually is going to be 4 sig figs. So I think I'm just going to plug this in and leave 4.7451. Now, if I multiplied by 100, it's kind of like saying this sample, any sample of lead chloride should be about 74.5% lead by mass. If I multiply by 100, I'm like moving the decimal spot 2 places. So approximately 74% lead in any sample of lead 2 chloride. You may recall something called the law of definite composition, which says that any sample of lead chloride, if it's going to have the same properties, then it has to have the same composition by mass. And by atomic structure, we have to have the same elements in the same ratio, which should lead us to the same composition by mass. So I'm going to leave it as a decimal because then if any sample of lead chloride is about 74% lead, let's just multiply by my sample size. I've got 25.80 grams of that lead chloride. And it's about 74%. So if we leave it as a decimal, we can just multiply across. We should have about 19.22 grams of lead. That's where I left the 4 sig figs. The original measurement was in 4 sig figs, so I'm going to leave 4. And again, that's why that 0 at the end is important. When you set this up, don't just say 25.8. That 0 gives us an extra sig fig, which could be important in the end. So again, we could have done this with some stoichiometry, and we could have written a balanced equation. But this is kind of handy if you kind of recall this percent composition and the law of definite composition. You can say any sample is going to have a particular composition by mass, and we can just apply that to our sample size. The last one in the section is fun. Usually people look at this and they'll be like, I'm not going there. Oh, actually, it's not that bad. This is going to refresh our memory on some balanced equations a little bit, specifically a combustion. We've got an unknown compound that reacts with oxygen. Carbon dioxide and water are collected. And they give me all the masses. What mass of carbon must have been present in the original sample? Do you recall combustions a little bit? It's some kind of an organic compound. Organic meaning like a carbon compound. Organic compound. It's reacting with oxygen. Oxygen gas is diatomic. And the products are always carbon dioxide and water. Oh, yeah. Combustions are usually kind of fun. Something's burning. They're exothermic. Now, the fun part about this one is that we don't know the identity of the original compound, so I can't really balance the equation or anything like that. I don't know how many carbons or oxygens or hydrogens were present. I do know some mass data. Let's see if this helps us at all. We've got 0.1156 grams of this unknown compound. It's reacting with oxygen, so they're not telling me exactly how much. I do know the amount of products formed, 0.1638 grams of carbon dioxide, 0.1676 grams of water. Okay, so this organic compound, that's where the carbon would have been present. Where is the carbon present on the product side? Only one spot. All the carbon from this original organic compound is now present in the carbon dioxide. Oh, so you may recall the law of conservation of mass, which says that in a chemical reaction, mass cannot be created nor destroyed. So if I could figure out how much carbon is present in that carbon dioxide sample, it must be the same as the amount of carbon that was present in the original sample. We can't create or destroy extra carbon atoms. All the carbon from the original organic compound is still present, but now it's in the form of carbon dioxide. Oh, well, why don't we kind of do what we just did with that last lead compound? Let's figure out the percent carbon in carbon dioxide. Well, that wouldn't be so bad, right? Look up carbon, about 12.01. Let's divide by that, by the mass of the compound. So we'll add the 2 oxygen and say about 44.01. Now again, if I wanted, I could multiply by 100, but I think I'm going to leave this as a decimal. And I really don't have a lot to go on for sig figs, but if I look back up in the problem, all the original measurements are 4 sig figs. So I think I'm going to leave 4 right away here. 0.2729. So any sample of carbon dioxide is about 27% carbon by mass. We can just apply that to our sample. It's small. Let's multiply that by the 0.1638 grams of carbon dioxide. But that should tell me the amount of carbon in that carbon dioxide product. This one I'm going to definitely leave 4 sig figs. Ooh. Okay, it's small. 0.0. That leading 0 does not count. So I still get 4. 7. 0. Look at that. The leading 0 does not count. That's a placeholder. But a 0 at the end would be a significant figure as long as there's a decimal spot somewhere in the number, which there is. Hey, guess what? I'm done. That's my final answer. All the carbon in this carbon dioxide is the same amount of carbon that was present in the original carbon sample. So I kind of answered my question indirectly. I found the mass of carbon present in the carbon dioxide product, but that's the same as the amount of carbon present in the original sample. Well, that wasn't so bad. We just had to kind of recall that law of conservation of mass. It says carbon can't be created or destroyed. So if we know how much carbon is in the product, we know how much carbon must have been in the original sample.